All right, so welcome to your final unit of AP Physics 1. And this unit is kind of split into two main chunks, but they're part of a big whole, and that is electronics. And electronics, we're going to start with a really basic introduction into electrostatics, which has to do with the study of charge and understanding charge and attraction and repulsion. And then we'll actually only briefly look at that, and the vast majority of what we're going to do in this class is going to be analyzing some very basic DC circuits. So some of you have done DC circuits before in other classes. Maybe you did resistors in series, resistors in parallel if you've taken any of the engineering classes. And we'll get a nice little introduction into that. And what's actually cool about that is it applies directly into household electrical systems. So what you learn in this class can actually help you in understanding what's going on in your house in terms of electricity. Now, if you come back and you take AP Physics 2, we get more in depth with electrostatics. We'll talk more about electric potential energy. So we get way more in depth with that. And then we also get a little bit more in depth with DC circuits. So in AP Physics 1, we're just going to be doing resistors in series and parallel. In AP Physics 2, we get into capacitors, which are a different electrical component. And then we'll also get into RC circuits, which are resistor capacitor circuits. So if you come back and take Physics 2, we get a little bit, that's like our third unit of the year, I think. We get more in depth with some of these topics. So you should start by watching pre-lecture video 1, which is on charge and force. And we're going to get right into talking about charges and forces. So when we're talking about charges, like normally we do some experiments during class, and we can do these experiments with a couple of really basic things. So we use glass rods and plastic or rubber rods, and wool and silk, and some of you have done this before. Maybe you blew up a balloon and you like rubbed it on somebody's hair and the hair stuck to the balloon, right? So we're going to use these basic things and we can do some experiments. Now, since this is a video, we'll have just some visuals for that. So here's one experiment. If you take two plastic rods and you bring them near each other, and those plastic rods have been undisturbed for a long time, and we bring them near each other, nothing really happens. And the reason nothing happens is because both of these objects have been sitting and they are plastic, they're both plastic, and they are neutral, so they have no charge. So what we interpret from that is that if there's no special electric properties for something, we call that object as being neutral. Neutral means no net charge. Does it mean there's no charges? No, it doesn't mean that at all. It means, though, if we have positive and negative charges, which we're going to be talking about this quite a bit, the amount of positive to negative charges are even. And we'll get more into what a charge is moving forward. So here's another experiment. I'm going to take that same plastic rod as I had before, and I'm going to rub that with wool. Or I'll take a glass rod and rub it with silk, and I'm going to rub both objects. Now, when we bring them near each other, the hanging rods move away from the handled rod. So these two rods essentially are repelling each other. And in real life, you've seen this before, right? With magnets, right? Magnets like to repel each other. If I have a north pole and a north pole, or a south pole and a south pole, those magnets repel each other. And this is similar to that, where we could treat this like a north pole, and we could treat this like two south poles, and they will repel each other. So the interpretation is, if I rub a rod, somehow it changes the properties that are going to create a force that acts between the two rods. And we've talked about this force earlier in the year when we first introduced forces, but this is known as a long-range force because it doesn't have to be touching it to happen. So somehow we're creating this force by the act of rubbing the rod. So we call this process of rubbing, we call that charging. We're charging the rod, and then we say that the rubbed rod is now charged, or that it has acquired a charge. So we charged it by this rubbing it with either the wool or the silk. All right, so what happens when we start to go either closer or further away from the rod? Well, we get a higher force or a larger force or a smaller force, and that's because this is a long range repulsive force, right? So it doesn't have to touch, but the closer it is, the larger the force that you experience or that the rods experience. So when we're looking at the electric force, which is what I mentioned already, the electric force is the force between two charged objects. So it could be multiple charged objects as well. We talked about gravity before too. Gravity is a long-range force as well, but it's always attractive. Two planets, if they have mass, are always attracted to each other, right? That's the gravitational law of attraction. Now, an electric force can be attractive or it can be repulsive. So here's another experiment. We instead of having two plastic rods or two glass rods, we have a plastic rod with a glass rod. And what we've noticed with these is that they will attract to one another. And that's because these are oppositely charged. So we can explain that we have two different kinds of material, and we assume that then they're getting two different kinds of charge. Maybe one's a positive and one's a negative charge. So one is becoming positive and one is becoming negative, and opposite charges attract. So like charges repel, repulsive forces, opposite charges will have attractive forces. And we've already mentioned this already, but if we've increased the distance, the force between them, or the force that is felt, decreases. And you can try this with magnets, right? As I have two magnets, the closer and closer I bring them, the stronger and stronger that attractive or repulsive force is, so the more that I can feel it if I'm holding the magnet. Or if I have strong enough magnets, they might be far apart, but as I move them closer and closer together, all of a sudden they jump together, right? And that's because they're attractive force. And it's the same thing with charges. So like the gravitational force, the electric force decreases with the distance apart. The further away you are, the less that force. All right, so I got a quick check for you, and unfortunately I already have the answer. Charged glass and plastic rods hang by threads. An object attracts the glass rod. If it's held near the plastic rod, what'll happen? We actually don't know, because an object that attracts a rod, if it attracts it, it could be, we assume that it's probably oppositely charged, right? So we would assume that it would repel the plastic rod. However, we don't know enough about this situation. So what I could have actually is it could be a neutral charge. And we'll talk about this concept, but a neutral object, if held near a charged object, can be attractive. That's something known as polarization, which we'll talk about later. All right, so here's another one. The rod attracts a positively charged. Again, it could be, this rod could be negative or it could be neutral. So both of these are possible answers. So when we're looking at what a charge looks like, we're going to make charge diagrams. And your first lab, actually, is one that I came up with a couple years ago. You're going to be making a comic strip about the 3 common methods of charging. And you're going to be making charge diagrams. Now, these charge diagrams give a schematic picture of the distribution of charge on an object. So if we have a negative charge, we'll have minus signs. If we have a positive charge, we'll have plus signs. And if I have more and a lot, or more and more and more negatives, or more and more positives, that's going to represent a stronger and stronger charge, and less will represent a weaker and weaker charge. So when I start with a neutral plastic rod and a piece of wool, I will rub the plastic rod with the wool. So initially, both of these two, there's my positives and my negatives, right? Initially, both of these two are neutral. So there's some positive and some negative charges. They're neutral. So I can make a charge diagram which acts as a schematic to show that they're neutral. So now, if I charge them, all of a sudden, my plastic rod and my wool are going to attract each other. And why is that? Well, let's take a look at the charge diagram. Well, if the charged plastic rod, for example, is becoming negative, where are those electrons coming from? Well, the electrons are coming from the wool, and they're being added to the plastic rod. So if electrons are leaving the wool, what's that going to leave it with? It's going to leave it with a positive charge. So if I have a negative rod and positive wool, those two things are going to attract. So when we rub a rod by wool, not only does the plastic rod acquire a negative charge, but the wool will also acquire a positive charge. So a neutral object is going to be equal amounts of positive and negative, and it can give off some of those charges to something else, and then it will have excessive charge of the opposite. So if it gives off the negative charge, it'll be left positive. But a neutral object is equal amounts of positive and negative, and both objects started that way. So an object can become positively charged if there's more positive than negative charges. Or similarly, an object can become negatively charged when it has more negative than positive. Now, there is a golden rule for this, and that is that electrons are the only things that can move. And we'll talk more about that as we go through this unit. So when I'm visualizing this first charge, right, I have my plastic rod, it's neutral, my wool is neutral, right? So here is a picture of that. They're each neutral. Now, as I, in step 3 here, rub the rod, some of the electrons from the wool are being transferred onto the rod. So this rod is picking up electrons. So in picture 4 here, we can see that there's 1, 2, 3 protons, but 6 electrons, or 6 negative charges, I should say. We haven't talked about that yet. So 6 negative charges, but only 3 positive charges, which means that this is a negative charge. And then oppositely, I have positive charges on the wool that outnumber the negative charges. So this is positively charged. And we can simplify that and get rid of all the extra stuff and just say, all right, well, let's just make the wool positive and just give it 3 positive charges, and the rod negative and just give it 3 negative charges. Now, does that mean there are no positive and other negative charges? No, it's a nice way, it's a nice visual of showing that there is an excessive charge on each one. We don't have to draw every single particle, right? That'd be impossible. So the law of conservation of charge states that the charge, just like the conservation of mass, is never, or energy, is never created or destroyed, only transferred from one place to the other. So if I have positive charge somewhere, an equal amount of negative charges must be somewhere else so that the net charge does not change. So when I rub the rod to charge it, electrons are moving over. They're not destroying protons, we're just transferring electrons. Now, we'll talk a lot about some insulators and conductors. So if I have a metal sphere can acquire a charge from a charged piece of plastic. So if we charge a piece of plastic and rub it with wool, we touch it to a neutral metal sphere. The metal sphere will then afterwards repel that charge. Why? So if this is a negative charge, it's going to rub off some negative charge on the metal, and that'll be a negative, and now those two things will repel each other. So in class, we do a lot of experimenting with pith balls, or I'll do some demonstrations with pith balls, which are little metal spheres, and we can easily see charge and what happens with charge there. But I could expand on this experiment, and I could bring this charged plastic rod here and touch it to the metal, which we know is going to be negatively charged. But then this other metal sphere over here remains neutral. So what happened? Well, the charge was transferred to the metal sphere, but in between, I have this plastic rod that's touching both of them. Well, the plastic rod is acting as an insulator, which an insulator does not allow charge to flow. So whenever we have wires, like your headphones have wires in them, right? And there's like a plastic-ish coating around your headphone wires, and that is because it's an insulator. If you didn't have that, those wires are having electrical current running, you could get shocked. So that the plastic is acting as an insulator. Now, if I take that plastic rod out and replace it with a metal rod, now I can transfer charge across. And why? Because this metal rod in the middle is acting as a conductor. A conductor allows charge to flow. So insulators and conductors. Charge can be transferred from one object to another object via touch. Discharging is removing the charge from an object, which you can also do by touching it. So we'll talk about something called ground. You can be a ground when you touch a charged object, such as somebody is in socks and they rub their feet on carpet and they touch you and it shocks you. What they're doing is they're building up excess of charge, and then they touch you and they are discharging to you who do not have those excessive amount of charges, and therefore the charge flows from them to you and causes a shock. Conductors allow charge to move easily. So conductors, they allow things to flow. If you think about somebody conducts a train, the train's moving, the charge can move. Insulators, charge cannot move. Now, glass and plastic rods are insulators, but then how do we get charge on them? Well, we force the charge on them by charging through friction, and then it becomes a very good constant charge because it doesn't allow the electrons to flow. So metal is a good conductor. There are a lot of good conductors. Most of the wire in your house is copper wire. There is some wiring that is aluminum because it's a lot cheaper. So if I need really, really thick wire, a lot of times electricians will use aluminum wire. The downside of that is oxidation. So they have to take extra precautions to make sure that that aluminum wire doesn't oxidize as it's being used and deteriorate. So copper wire is still the gold standard for electrical wiring, but it's also really expensive. So it's the gold standard, but it costs a lot of gold. All right, as we continue to kind of go through and get some basic definitions and vocabulary, if we're in equilibrium before, we've talked about equilibrium, right? We don't want to go to the left or to the right, or our forces are balanced, whatever you want to say. Well, that's when the charges are balanced. So there's no excessive positive or negative charges. So a conductor will be in electrostatic equilibrium unless there is an adjustment of charges. So it doesn't mean that the object is not charged. It means that charge is not flowing. So I could have an electrostatic equilibrium. So if I have the metal sphere here and it's neutral, and I bring my negative rod here, right? Right now, these are both in electrostatic equilibrium, even though my rod is negative. Now, as I touch the sphere, some of those negative charges are going to transfer to the sphere. And because there are still positive charges in here, these molecules will rearrange each other because of the laws of attraction and repulsion. But eventually, it'll be at electrostatic equilibrium, meaning that the charges are not shifting around, but they're evenly distributed as best as possible with that law of attraction and repulsion, and it'll still have a net negative charge. All right, so our first lab is going to be getting into three main methods of charging. The first method is polarization. And polarization isn't actually transferring charge. It is a slight separation of positive and negative charges on a neutral object. So here I have a neutral sphere. Now, if I bring a positive rod close to that neutral sphere, we know that opposite charges attract. So in this neutral sphere, because it's conductor, it allows charge to flow. So the electrons will flow to the side closest to the rod, and that'll leave a net negative charge on this side. Well, they're leaving the bottom side, so that will leave a net positive charge on the bottom side, which means that one side is negative and one side is positive. But as soon as I take this rod out of there, those charges are going to redistribute it. So polarization is a temporarily induced charge separation of positive and negative. And there's actually some cool things that we can do with this. If you have a balloon at home and a sweater, blow up the balloon and rub it with the sweater. Make it nice and staticky and stick it to your wall. It'll stick to the wall because of this concept of polarization. So when we bring a rod close that's being polarized to a sphere, there will be an attractive force that will the positive rod will attract the negative particles. Well, let's think real quick though. What if my rod was negative? Well, then the negative charges would move away to the other side, and I'd have a negative rod, and I'd have positive up front. So would they attract or repel? It would still attract. So that's why attraction isn't the best way to judge the charge of an object. So if I know that it's a positive charge, like my rod initially was, and I brought it near a neutral object, it's still attracted. But if I have a negative charge and bring it to a neutral object, it'll still be attracted. So attraction is not the best way to judge the charge of an object. It's also not the best way to judge a person. So polarization is a force between a charged object and a neutral one, and it is always attraction. The particles are slightly separated, not because that they're positive or negatively charged, but there is a charge separation. So we'll talk more about some different types of charging going forward. We talked about polarization. We're also going to talk about conduction, which is charged by touching, and induction, which is a little bit more confusing. It's kind of a combination of it's a combination of polarization and a little bit of conduction, but kind of in a weird way. Induction is actually charging by grounding. So we'll talk about that a little bit more later. We're also going to talk more about the concept of what a charge is at the molecular level, and that'll help us better understand what's going on. And we will do that in the next segment.